To make an ionic compound, you need one metal and one nonmetal. To write a chemical formula, you use their chemical symbol. When you write it, the metal always goes first and then the nonmetal. The sum of the charges of an ionic compound must always equal 0. If it doesn't, then you must add additional ions until it is balanced. Magnesium sulfide is balanced with one of each other. So, this one has a positive 2 charge, this one has a negative 2 charge. So, it would be written as magnesium sulfide. But, if you have chlorine particles, and chlorine has a charge of -1, so you'll need 2 to balance out the formula, which would be written as magnesium chloride, with a small subscript 2 to show how many ions are in the formula. Ionic compounds can also be written in words. For magnesium chloride, the written version would be magnesium chloride, and you don't have to include the subscript when you write it. A polyatomic ion is an ion that can have multiple different charges. Take rhenium here, which has its most common charges as +4 and +7, and it can be others, but these are what you'll most often find it as. To write one, you'll often show it by writing the word version and having gold as an example, and then its charge as a Roman numeral, and then the gas. You don't show the charge here in the symbol formula. A polyatomic ion is an ion made up of a group of atoms. For example, strontium sulfate is written SrSO4, since sulfate is SO4. And this is balanced, so you can leave it as it is. Just like a normal ionic compound, a polyatomic ionic compound must have a charge sum of 0. So that means we have to add another nitrate. So to do that, would we write just like this? Well, no, because that means there would be 32 oxygen in there. So what you actually have to do is write a bracket around the nitrate and then write the 2 there. So now it's balanced. A multivalent polyatomic ionic compound is a culmination of what we've learned. So here we have niobium 5 citrate. And since niobium has a charge of +5 and citrate has a charge of -3, we need 3 niobium with a charge of 5 to have a positive 15, and 5 citrate with a charge of -3 to have a -15 charge, which brings it out to 0. This is how you'd write a polyatomic multivalent ionic compound.
This is how you name ionic formulas. First, you have your formula. For example, CaO, which you can see on your periodic table is calcium and oxygen. Calcium on the periodic table is a metal, so you know that this will be ionic. And oxygen on the periodic table is a nonmetal. So to write this, you would put calcium oxide, because when you have a metal and a nonmetal, the nonmetal at the end you take off for oxygen, YGEN, and put ide. So that is how you name a simple ionic formula. This is how you name multivalent ionic formulas. First, you have your formula, which in this example I shall be using copper, which is Cu, fluorine, which is F. The charge for fluorine is 1, so there's nothing next to the copper. And for copper, since it's multivalent, which means it has more than one charge, fluorine will have a 2 next to it because it crisscrossed. So to write this and name that ionic formula, multivalent ionic formula, you'll have to put copper in brackets the Roman numeral 2, because this is the charge we're using to name this multivalent ionic compound, fluorine. And that's an example of a multivalent ionic compound.
Similarly to the elements of the periodic table, there are a number of preset combinations of atoms known as polyatomic ions. These polyatomic ions have a set charge and formula just as the other elements of the periodic table do. Polyatomic ions are all negatively charged, except for ammonium, which is the only polyatomic ion with a positive charge. So you can usually treat polyatomic ions as a non-metal in all compounds. In this case, you can see that the aluminum is +3 and the phosphate ion is -3. Therefore, they link together, making an ionic compound. In the case of a polyatomic ion, however, you can't just look at the periodic table and find the formula. You have to look at the polyatomic ions chart, such as this one. You can then look for the formula and find your polyatomic ion and its name here, so you can name the compound. In the case of this phosphate ion, we can look at the chart right here and look for PO4, which is the formula of phosphate. Once we find PO4, which is right over here, we can go across and look that it says phosphate. Once we have found out that PO4 is in fact the formula for phosphate, we can go ahead and name it just as we did with the regular elements, but leave the polyatomic ion's name just the way you found it. So we can take the metal, which stays the same, aluminum, and phosphate, which doesn't change because it's a polyatomic ion, as phosphate. As a result, we can name this aluminum phosphate, just as you can see here. In the case of this compound here, we can clearly see that chromium phosphate is a compound that can exist because this chromium has a +3 charge and the phosphate has a -3 charge. In this case, however, now that we don't see the charges, we can't just thoughtlessly decide that Cr is chromium and PO4 is phosphate, so we can decide that the name is chromium phosphate. It doesn't work that way because if you look on the periodic table, you will see that chromium has more than one charge. As you can see here, chromium has a +3 charge and a +2 charge. We can also look at the chart of polyatomic ions to find that the charge of phosphate is -3. When looking at this formula, we can see that there's only one atom of chromium and only one polyatomic ion of phosphate. In this case, if we have chromium 2 and phosphate, which has a charge of -3, they don't balance out and can't make a compound together. On the other hand, if we have chromium 3, then we can link it with phosphate, which has a charge of -3 and balances out to 0. That's why in the case of naming this formula, we must determine that we are using chromium 3 in the compound instead of chromium 2. So we would then name it like this. And then write phosphate normally. As a result, we can name this compound chromium 3 phosphate.